Hi everyone, this is Dr. G. Ravindranath Reddy, working as Assistant Professor of Mathematics in MLR Institute of Technology, Hyderabad. So here we are going to discuss a course, Numerical Methods and Integral Transforms. In that course, we are going to discuss the first concept, that is interpolation. Now in this video, we will see what is the introduction to the interpolation, where you can use this interpolation and what is the meaning of this interpolation, and some applications we will see on interpolations. So first we will go for the definition of interpolation. So interpolation is nothing but a method which is used to find out the value of y at a given particular value of x when the given function is unknown function. For example, I'll explain this interpolation concept with an example here. So let us take one. So I'm taking this table here. So I'm taking x values and y values 0, 1, 2, 3. I'm taking a function y is equal to x squared. So now once if you know the value of x here, we can substitute this x value in this relation and we can find out the value of y. Now when x is equal to 0, if you substitute x is equal to 0 in this relation, we will get y value is equal to 0. And similarly, you take x is equal to 1 and get the value of y, that is also equal to 1. And next, like this, if you substitute this x is equal to 2, you will get y is equal to 4. And if you take x is equal to 3, we can get y is equal to 9. So this is very simple. So whenever we know the values of yes, by substituting that values in this relation, automatically we can get our required y values. Okay, now we'll take one more function, one more table here. So y values 0, 1, 2, x values 0, 1, 2, and now we have to find out the value of y. So the relation is f of x, and we don't know what is the value of that f of x here. So y is equal to f of x. This is, we don't know the function f of x, whether it may be unknown function. So whenever we want to find out the value of y for the unknown function, then definitely it is not possible to get the value of y, even though if you know the value of x. But we can find out the value of y when x is equal to 0, even though the function is unknown. So the process of finding this y value at a given particular value of x for an unknown function is, we can call it as an interpolation. So interpolation is nothing but the process of finding the value of y at a given particular values of x for the unknown function. F of x is an unknown function. So for unknown function, if you are able to get the value of y at a particular value of x, this is possible only by using the concept of interpolation. Okay, this is a best example where you can use the concept of interpolation here. Similarly, we will take another example. So this is the table of x values and y values. So 0, 1, 2 and 3. At x is equal to 0, imagine 2, 1, 2. And now at x is equal to 0, he has given the value of y as 1. When x is equal to 1, we know the value of y as 2. And x is equal to 2, we don't know the value of y. And when x is equal to 3, we got that y value is equal to 9. So now when x is equal to 2, we have to get the value of y. And the function, we don't have the unknown function. We have unknown function, that is y is equal to f of x. So now whenever we want to find out the missing term in the given table for an unknown function, then we can also find out this missing term by using the concept of interpolation. Okay, so this is the best examples for interpolation concept here. So whereas this total interpolation concept is based on the finite differences. So in these finite differences, it includes forward differences, backward differences, and central differences. So these three we can consider as a standard examples of finite differences here. So by using these forward differences, backward differences, and central differences, we are going to find out the value of y at x is equal to given value at a particular value of x for unknown function. By using these three concepts, we are going to find out here. So first in this video, we'll discuss what is a forward differences, how to construct the forward difference table here. So later we can go for the backward difference, what is meant by backward difference, how to construct the backward difference table, and what is meant by central difference, how to construct the central difference table. So now we'll concentrate on the forward differences here. So I have taken the function y is equal to f of x, which in this x we can consider as x as an independent variable here. So for y, I have considered some values y0, y1, y2, y3 and so on, yn. So these are the values of y corresponding to the values of x. These are the x values I have considered x0, x1, x2, x3 and so on, xn respectively. So when we take x is equal to x0, then y value we have to consider as y0. When we take x is equal to x1, we can consider this y value as y1. So for each corresponding values of x, we are having its corresponding y values here, y0, y1, y2, y3 and so on, yn. Now here, if you construct a table here, so x1, x2, x3, x4 and so on, and its x0, initial value is x0, so its corresponding y values are y0, y1, y2, y3, y4 and so on. So now you concentrate on this y values here. Now first you take first two values of y, y0 and y1, and find out the difference between these two values. So the difference is second value minus first value, that is y1 minus y0. So this difference of y we can consider the forward differences of y. And next similarly take this next two values, y2 minus y1. Next you take the next difference values, you will get y3 minus y2. And similarly you take all the values of y and find out the differences of its values. So y4 minus y3. So this difference y1 minus y0, y2 minus y1, y3 minus y2 and y4 minus y3, and these or we can call it as a first forward differences of y values here. So these y differences are represented with y1 minus y0 is represented with delta y0, and y2 minus y1 is represented with delta y1, and y3 minus y2 is represented with delta y2 and so on. We can represent this. So these differences we can call it as a first forward differences of y values here, and these first forward differences are represented with delta y0, delta y1, delta y2, delta y3 and so on. So where this delta we can call it as a forward difference operator. And similarly, whatever the differences we got, once again if you find out the difference of that difference values, so we have represented this y1 minus y0 with delta y0, and y2 minus y1 we have represented with delta y1, and this y3 minus y2 we have represented with delta y2, and y4 minus y3 we have represented with delta y3. So these are the differences of these y values here. Now once again you find out the difference of these resultant values. So delta y1 minus delta y0. So the differences of first forward differences we can call it as a second forward differences of y values. And next you take the next pair, delta y1 and delta y2. You find out the differences of these values. We can call it as a second forward differences of y values here. So these are represented with, so delta square y0, delta square y1. So this delta square represents the second forward differences of y. So this delta square y naught is given by delta y1 minus delta y naught, and similarly delta y2 minus delta y1 is represented with delta square y1. So like this we can find out the differences of first forward differences. We will get second forward differences values, and whatever the values we got in the second forward differences, once again if you find out the differences of these values, delta square y naught, delta square y1, delta square y2, delta square y3, these are the values you will get in the second forward difference column here. So if you find out the, once again if you find out the differences of this, you will get our third forward differences of y values here. So like this we have to continue finding the differences until we get a single value in that particular column here. So in general the second forward differences are represented with delta square y suffix r is equal to delta y suffix r plus 1 minus delta y suffix r, where all takes the values 0, 1, 2, 3 and so on. So if you continue like this, we will get nth forward differences of y values here. So whatever we have discussed now, if you represent all these things in the table, we will get our forward difference table here. So these are the values of x we have considered in the previous slide. So x0, x1, x2, x3, x4, and its corresponding y values y0, y1, y2, y3 and y4. Now I want to find out the first differences of this. So it is represented with delta y. So how will get this delta y values first forward? You consider these two pair values here, y1 and y0. So y1 minus y0 is represented with delta y0. Next you take the next values here, y2 minus y1, it is represented with delta y1. And next if you take the next pair y2 and y3, find out the difference y3 minus y2, then it is represented with delta y2. So like this, if you find out the differences of all the values of y, you will complete our first forward differences of y, which is represented with delta y. Now in this present column, the resultant values are delta y0, delta y1, delta y2 and delta y3. Now once again you find out the differences of these values here. These are the values, resultant values in this present column. Now if you find out the differences of these values, then we can get our second differences of y values, which are represented with delta square y. So first value is delta y0, second value is delta y1. Find out the differences here. Delta y1 minus delta y0 is represented as delta square y0. Next you take these two values here, delta y2 minus delta y1. This difference is represented with delta square y1. And similarly you take the next two values here, delta y3 minus delta y2 is equal to delta square y2. So this delta square y0, delta square y1 and delta square y2, these are the resultant values in this second forward differences of y values. Now whatever the values we got in the second forward differences, once again you find out these differences here, we can get our third forward differences, which is represented with delta cube y. So we have to follow this procedure until we get a single value in that particular column. So if we get a single value here, then it is not possible to go for the next column here, because it is not possible to find out the difference, since we are having only a single value here. So this is the way how we can construct the forward difference table here. So this is the standard format of forward difference table. So now let us take some examples on the forward difference table, how to construct the forward difference table by taking some examples here. So the first problem is, we have to form a forward difference table, and after constructing that forward difference table, these are the values we have to find from the forward difference table. So this is the data given in the problem, x values and y values. So x takes from 1, 2, 3, 4, 5, 6, and here whenever we want to apply the forward difference or backward difference or central difference, the difference between the values of x must be similar. Suppose if we take 1 and 2, the difference is 1. and if you take next 2 and 3, the difference is 1. If you take 3 and 4, the difference is 1, and if you take 4 and 5, the difference is 1. So for all these values, the x values, we must have a common difference between the values of x. Then only these forward differences or backward differences or central differences are applicable. Okay, so now this is the data given, and now we'll see how to represent this forward difference table for the given data here. So now whatever the values of x and y are given in the problem, I have taken these x values and y values as a 2 columns. Now I'm going to find out the difference of these values. So what we discussed in the previous slide, follow the same procedure here. Y1 minus y0, so it becomes 8 minus 1, 7, and 27 minus 8, you will get 19. 64, find out the difference of these two numbers, you will get 37. Next, 125 minus 64, you will get 21, and next take the two values 125 and 216, you will get the difference of these values as 91. So this 7, 19, 37, 61, 91, these are the first forward differences of these values here. So we can represent this value as delta y0, and we can represent this as delta y1, and this 37 is represented with the delta y2, and this is delta y3, and this is delta y4. Now find out the difference of this. Now we can use the calculators and we can find out these values here. So 19 minus, now take the calculators and find out 19 minus 7, we can get this value is equal to 12. So 37 minus 19, you will get 18. So write these differences in between these two values here. The difference of these two numbers is here, and take the difference of this 61 minus 37, you will get these values is equal to 24. Next, 91 minus 61, that is 30. So these values are represented with, since it is a second forward differences, it is represented with the delta square. So delta square y0, delta square y1, and delta square y2, and this is delta square y3. Now find out the differences of these two once again in the next column. So 18 minus 12, you will get 6. So 24 minus 18, here you will get 6, and next 30 minus 24, 6. So these are represented with, since it is a third difference, so it is third difference is represented with a delta cube. So delta cube y0, delta cube y1, and delta cube y2. Now find out the differences once again for these latest values. 6 minus 6, 0, and here these two values equal to 0, and 0 minus 0 is also equal to 0. Now this is the forward difference table for the given data here. So the first part of the problem is completed, constructing the forward difference table. Now we have to find out the remaining part. So in order to find out the remaining part here, let us consider the function y is equal to f of x. So when we substitute x is equal to x0 here, you will get f of x0. That f of x0 value is represented with y0. So our x0 value in the table is 1, and its corresponding y value is given as 1, and similarly y1. So y1, you will get this y1 when we substitute x is equal to x1 in the function f of x, you will get f of x1. So that x1 value is given in the table as 2. So f of 2 value from the table we can get that f of 2, that is second value of y in the table is 8. So like this you find out this y2 value. So y2 is equal to f of x2. So that f of x2 value is given in the table as 3. So f of 3, its corresponding y value in the table he has given as 27. So like this you convert this f of x0, f of x1, or f of x2, convert these functions in terms of y0, y1, y2, y3, and so on. Now Our task is finding the value of f of 1, finding the value of delta f of 1, delta square f of 2, delta cube f of 3. These are the values we have to find out now. So now here delta, you keep that delta as it is, and f of 1, we can take that f of 1, that is nothing but x naught, f of x naught, that f of x naught is represented with delta y naught. So in the forward difference table, we got the delta y naught is equal to, in the forward difference table, we got delta y naught is equal to 7. So we have represented in the previous slide, delta y naught is equal to 7. And similarly, the second value, delta square f of 2, that f of 2 is represented with y1. So this can be written as delta square y1. The delta square y1 is nothing but the second forward differences of y. In that particular column, you consider the second value in that column. So that second value is 18. So delta square f of 2 value is 18. And similarly delta cube f of 3. So f of 3 is represented here. We got that f of 3, it is represented with y2. So in place of f of 3, I have replaced with y2. So we get delta cube y2. In the difference table, we got the delta cube y2. In place of this delta cube y2, we got the numeric value as 6. So once if you construct this forward difference table, then automatically from that forward difference table, we can find out all the values of this delta f of 1, delta square f of 2, and delta cube f of 3 value. So this is one example how we can construct this forward difference table, and from the forward difference table, this is the way how we can get these values given in the problem. So now let us take another example here. So how to find out the missing term in the following table. So this is the data he has given already while you are discussing the introduction to the interpolation. So by we said that by using this interpolation concept, we can also find out the missing term. Now we'll see how to find out the missing term here. So this is the data, x values and y values he has given. When x is equal to 3, we have to find out the value of y, that is the missing term here. So now here, this is possible, we can find out this by using the concept of a difference table. Now let us construct the forward difference table here for the given data. So whatever the missing term you are having in the problem, I have replaced that missing term with x, or we can take any alphabet. You can take a or we can take b, or you can take anything. So I have taken that missing term, I have represented that missing term as x here. Now similarly, in the previous slide we have seen how to construct this difference table here. Follow the same procedure. So 3 minus 1, this is 2, and 9 minus 3, 6. So 9 minus 3, 6, and we don't know the value of x, so x minus 9, and 81 minus x. So these are the first forward differences of y. And similarly, find out the differences of this 6 minus 2, second value minus first value. 6 minus 2, that is 4. And next, x minus 9 minus 6. So this can be written as x minus 15. And here 81 minus x. If you want, you can do this. So 81 minus x, that is second value minus first value, x minus 9. Remove this. 81 minus x minus of minus plus. So 81 plus 9, you will get this value is equal to 90 minus x minus x, we can take it as minus 2x. Now find out the difference of this once again. So you will get this value is equal to x minus 19, and once again you find out this difference here. So 90 minus 2x minus of x minus 15. So you will get 90 minus 2x minus x minus of minus plus 15. So 90 plus 15, you will get this value is equal to 105 minus 2x minus x, you will get minus 3x. Now once again take the difference here. So you will get 105 minus 3x minus x minus 19. So you will get 105 minus 3x minus x minus of minus plus 19. So 105 plus 19, you will get this value is equal to 124. 124 minus 3x to minus x, you will get minus 4x. So this is the last value in the forward difference table. So whenever we want to find out any missing term in the given data, whatever the value we got in the last forward differences of y, equate that value to 0. So our last difference is delta square y naught, and we have to equate that value to 0. That value is given by 124 minus 4x is equal to 0. Now simplify this, you will get our x value, that is x is equal to 31. So this is the way how we can find out this missing term by using the concept of forward difference table here. So in this session we have seen what is an interpolation, where you can use this interpolation, and what is the forward difference table, forward differences, how to construct the forward difference table. Now in the next video we will discuss what is Newton's forward interpolation formula, when we can use this Newton's forward interpolation formula with some examples here. So thank you all of you.